So dear student, in this session we will see what is the relationship between the van der Waals constant and critical constant. Let's see what is the van der Waals equation. You know, you have studied van der Waals equation in 11th or 12th standard. For 1 mole, it is P plus A upon V square into V minus V equal to RT. For n moles, you have to consider n, P plus A n square upon V square into V minus n B equal to nRT. So these van der Waals equation are applicable for real gases. For ideal gas, we have ideal gas equation, that is PV is equal to nRT. But van der Waals modified this equation by making pressure and volume correction, by considering the force of attraction between the molecules and also the volume occupied by the molecules. So he incorporated these two constants A and B, and this is the van der Waals equation applicable for real gases. So we'll see what is the relationship between the van der Waals constant, that is A and B, with critical constant Tc, Pc and Vc. Please remember this: Tc equal to 8A upon 27 Rb, Pc equal to A upon 27 B square, Vc equal to 3B. I think these three, if you remember, that's fine. You don't have to write in terms of AB and Tc, because whichever way you write, it's fine. Okay. Now if you see this is the relationship between PC, BC and AC, you can write in terms of AB or you can write in terms of TC, PC and VC. Anything would be fine. So these three easy to remember. TC equal to 8A upon 27 RB, PC equal to A upon 27 B square, VC equal to 3B. The relationship between the van der Waals constant and the critical constant. We'll see how to derive this using isotherm of carbon dioxide. Okay, it is mentioned isotherm of carbon dioxide. It can be applicable for any gas. We will consider only the isotherm of carbon dioxide. Isotherm means that is temperature is constant. You have to plot pressure versus volume. So at various constant temperature. Okay, 13 degree, 21. You know, at 31 degree, which is a critical temperature of carbon dioxide, at this temperature, both gaseous and vapor phase coexist, and it is the maximum temperature above which you cannot find the liquid phase of carbon dioxide even if you increase the pressure. So this is the critical temperature. So at this junction or at this point, so that if you write van der Waals equation or van der Waals isotherm in this form and take the derivative of pressure with respect to volume, of course it will be 0, because this is called point of inflection. Okay, first derivative and second derivative of this pressure with respect to volume. So delta P by delta V at constant temperature, it should be 0. Similarly, second partial derivative with respect to volume at constant temperature should also be equal to 0, because this is a point of inflection in this curve. So now we have rewritten, okay, you know, this equation that is van der Waals equation for 1 mole, you can rewrite in this form, okay, so as to take the derivative with respect to volume. Now you take the first derivative and second derivative of this equation. So what will be the first derivative with respect to volume? By keeping the temperature constant, it will take this form. Okay, so that RTC equal to 2A into Vc minus V whole square divided by Vc cube. Now, so you write the first derivative and rearrange it. The first derivative has to be 0 at this point of inflection. So rearrange this. RTC is equal to 2A into Vc minus V whole square by Vc cube it becomes. Now you take the second derivative, equate to 0 at the point of inflection. Rearrange this. Write RTC in terms of RTC, which is equal to 3 into Vc minus V whole cube divided by Vc raised to 4. Now this is also RTC. You have written this is also RTC. So equate these two from first and second derivative. So these two are equal. So this one, that is 2a into Vc minus b square divided by Vc cube, is equal to this. Now from this you can cancel some of this. You know, these are simple mathematical calculation. You can find out Vc, that is critical volume, which is equal to 3 times the B. Okay, van der Waals constant B. Now to find Tc, this Vc is equal to 3b. Just rearrange this. Vc minus b is equal to Vc minus b equal to 3b minus b equal to 2b. Now you know RTC is equal to, from this one, RTC is equal to 3a into Vc minus b. Now you put this value 3b. RTC is equal to, because 3b, this is Vc, okay. So incorporate this, 2a into 2b square divided by 3b raised to cube. So you'll get 8a upon 27b. So Tc is equal to 8a divided by 27b divided by r. So Tc equal to 8a upon 27br. So it's a relationship between critical temperature and van der Waals constant. To find Pc, so you go to the first equation. P is equal to RT upon V minus B minus A upon V square. Put Pc in that, because at critical pressure. And you know Vc minus B, okay, Vc equal to 3b. Put here, that becomes 2b. So this becomes 9b square is equal to 3b whole square. So rearrange this, okay, in terms of this RTC value you can put 8, TC value you can put from this 8a upon 27b, then RR gets cancelled, minus a upon 9b square, 8a upon 54b square minus a upon 9b square. So you can easily get this as a upon 27b square. So Pc is equal to a upon 27b square. So these are the direct relationship of critical constant with van der Waals constant. Thank you. Thank you for watching.